I'm going to share my screen and let's see if I can
Recording in progress.
Everything. So does this work?
Recorded start. Yeah,
Okay.
we can see your screen. Awesome.
Perfect. So welcome everyone. I'm happy to see some friendly faces in the audience. And it's my first time presenting here at IAFTI. My name is Bogdan Burlacu. I'm from Iași originally. I studied computer science at the Technical University in Iași, at the Gheorghe Saki Technical University, with my major in automatic control and science engineering. And since 2011, I have been joining the University of Applied Sciences, Austria, initially as a PhD student on a PhD scholarship. And since then, I've been working in the field of machine learning and optimization, and particularly on things that fall into the umbrella of scientific ML, like the title of today's talk, and which basically include all kinds of algorithms and machine learning techniques that allow us and our industrial partners to learn from data and to basically discover new physical things about industrial processes. So a little bit about myself. You can already see my profiles in there. If you have any questions at all, just shoot me an email after the talk. So I finished my education with Bachelor's of Engineering in 2009. I worked for a couple of years in software in Iași, Romania. Then I started working here in Linz, Austria, as a PhD student at the Johannes Kepler University in Linz, and then later as a research associate at the University of Applied Sciences, Austria. I received my PhD in computer science in 2017 with a thesis focused on symbolic regression, on more theoretical aspects, and on developing new algorithmic prototypes for symbolic regression. You can also Google and you will find the thesis itself. It's open access at the digital library of the Johannes Kepler University. And since 2015, I'm a senior researcher, and since 2018, I'm also a member of the Josef Ressel Center for Symbolic Regression, and I will present some of the work in our group today. I've also been teaching data preprocessing and analysis since 2018 for master students at the University of Applied Sciences, part of a curriculum called Human-Centered Computing. So basically, my interests lie in machine learning and data science, and of course also programming. So I'm a kind of pretty hands-on kind of person. Okay, so at our group, Heuristic and Evolutionary Algorithms Laboratory at the University of Applied Sciences, we are developing several open source projects in the area of optimization, so heuristic and meta-heuristic optimization. The biggest one is Heuristic Lab, which is a software that is now very mature, being developed for, I think, around 20 years. It started as a C# project, but we are slowly moving to make it cross-platform. It contains a large collection of optimization algorithms. Another project that we are developing is called Operon. It's pretty much specialized on symbolic regression at large scale. So it uses several fancy libraries and design choices to perform symbolic regression at large scale. It's implemented in C++. And I've also been working on a couple of projects related to validated numerics, numerical stability, vectorized statistics, so performing statistical operations really fast, and interval undefined arithmetic. If you go on GitHub, you can find more information about our projects. Now about today's talk. So I have to begin by saying this includes basically working results from the past 2 or 3 years. And the topics are pretty broad, so it's going to be more or less a overview, or more or less to say barely scratching the surface of what's been going on in this field. I will start with a small introduction of the research groups here in Austria, with a small introduction of scientific machine learning, and then with a few more details about symbolic regression, about why we chose symbolic regression and what we're doing with it, and then with a couple of examples. First from physics inspired ML with shape constraints, and then with an example in material sciences about interatomic potentials. Right. So by the way, I don't know exactly how the format is supposed to be, but I think we have enough time either to have questions at the end or to just ask questions as we go. In any case, I'll be happy to answer these questions. Okay. Yeah. Okay. So our research group, Heuristics and Evolution Algorithms Laboratory, first started in 2005 at the University of Applied Sciences, Upper Austria. These universities are called Fachhochschulen in Austria, so this is where the FH comes from. It includes 5 professors and a number of research associates, as well as interns and master's and bachelor students. Most of them choose topics related to optimization, of course, and implement their new algorithms and ideas using Heuristic Lab or using any of our other frameworks. We have a pretty reasonable research output, so the group is involved in several research projects and receives funding, partly from state institutions and partly from industrial partners. This research also resulted in more than 200 publications published, so peer-reviewed publications, more than 10 dissertations, and 60 theses. You can find a list of scientific and industrial partners here at our website. So basically our group consists largely of software engineers who cooperate closely with industry partners, and so we are able to deliver artificial intelligence solutions that fit the partner's needs and that solve specific industrial or physics-based problems or challenges. Okay. So about Heuristic Lab itself, it is basically an interactive framework for the development, analysis, and application of optimization methods. It has gone through several iterations where it has been rewritten from scratch with a better and better design. So now it mainly consists of a plugin-based architecture with distributed computing capabilities. Its main focus is on combinatorial and symbolic regression classification problems. So on the combinatorial side, you can find, for example, traveling salesman, knapsack, bin packing, vehicle routing, scheduling problems, and so on. And on the symbolic side, of course, regression and classification. It also contains a large collection of optimization methods, which include traditional optimization algorithms as well as Meta-Heuristics based on all kinds of other search techniques like evolutionary search, tabu search, simulated annealing, and so on. Okay, so I've been here in Austria for 10 years already, and I've also been a developer of Heuristic Lab for 10 years. I have worked on many interesting optimization problems together with my colleagues. This is a non-exhaustive list of problems. A few of them I have worked on myself, some others my colleagues work on, but basically everything to do with operations research and with all kinds of optimization in the industrial sector. For example, production scheduling, stacking in steel industries or container terminals. For example, a steel plant has huge metal slabs that need to be stacked efficiently. In warehousing operations, in even cooperation with hospitals for cancer diagnosis based on tumor marker data, then in material science, properties of synthetic materials, in predictive maintenance and prescriptive analytics, and of course in modeling all kinds of physical processes based mainly on virtual sensors like exhaust gases, blast furnaces, firefighter vehicles and the foam quality from them, plasma retarding, the efficiency of recycling machines, and so on. So all this research is basically a process that involves, of course, fundamental research as well as a consistent part of software engineering, and as well close cooperation with domain experts, so that the solutions that we provide are continuously validated and ensured to fulfill all the expectations from a physical perspective as well. So I should mention all of this. This work is in a very pragmatic field, where of course the main interest of the entities involved, particularly the companies, is to make money. So as a result, our approaches are also very pragmatical, and they focus on knowledge discovery and insight into the industrial process. Okay. Now, since 2018, I've been a member of the Josef Ressel Center for Symbolic Regression. This was founded as a joint project between the Christian Doppler Research Association in Austria and the University of Applied Sciences Oper Austria, as well as a number of industry partners. First AVL and MIBA, and then later IRIMA, a company that manufactures plastic recycling systems. The head of the Josef Ressel Center for Symbolic Regression is Professor Gabriel Kromberger, and the focus of the group is to develop symbolic regression as a technology. So as a technology that can be applied in specific use cases in the industrial domain in order to bring value to the respective process. So part of this endeavor to develop symbolic regression as a technology, we are focusing on algorithm design, a symbolic regression that is high performance, that is deterministic, that is very accurate. We are focusing on method development as well, so this involves a lot of classical, if you will, computer science, knowledge and application. From an optimization standpoint, the methods should be easy to use, their number of parameters should be kept low, and last but not least, we are focusing on the integration of physical knowledge. And here I will have an example later in this talk about shape constraints. For more information, again, you can visit our website. This talk is intended to be more of an overview of everything that's been going on in this very rapidly evolving field of scientific ML. Okay, so a few words now about our industrial partners. The first company, AVL, focuses on the development, simulation, and testing of powertrain systems, so in the automotive industry mainly. They have various installations consisting of virtual sensors, test benches, and the focus of our work for them was to develop algorithms for real-time control on control units and for reduction of testing and development times. So basically to improve their R&D process. And we have already, of course, delivered software solutions and algorithms that they have integrated into their own business intelligence pipelines. Now, MIBA, the other company partner, focuses on friction materials and components for friction systems. So these are the so-called tribological systems. This comes from Greek, tribo and logical. So tribo means friction, everything that has to do with friction and lubrication and so on, and logical science. So the science of friction, if you will. So for them as well, we are trying to model the ways that different materials and oils influence the quality of the process and the friction involved. We're delivering model and data warehousing solutions for typological systems, and we're helping with automatic validation, as well as to overall improve their R&D cycle. The RIMA company, the last company that joined our project, designs plastic recycling systems, which, so here as well, there is an entire science of taking the raw material that has to be recycled and basically transforming it, let's say, in an optimal way into a byproduct that can be more easily recycled. So these machines as well are very sophisticated. They include virtual sensors, and they include controllers and so on. And we have the data from these machines, and we're trying to improve the process to optimize its stability and its throughput. Okay, good. So, one second, I'm going to move now to the next slide. I wanted to just get rid of this right now. So all our work in cooperation with industry partners is more or less in the umbrella, under the umbrella of scientific ML, because we are always trying to develop algorithms and solutions that bring insight into the process and into the let's say industrial application that these companies have. So SciML is kind of a blend between traditional first principles-based mechanistic modeling and data-based, data-driven methodologies, machine learning algorithms. These mechanistic approaches from first principles mainly consist of systems of differential equations that model various physical phenomena. And then on top of this, we have machine learning algorithms, starting, of course, with the most popular ones, neural networks, kernel methods like support vector machines, tree ensemble methods like random forests, Gaussian processes, all kinds of regression, symbolic regression, and so on. Now, the main challenge in scientific ML is to kind of be able to integrate the physical knowledge that we have, the domain knowledge, which is described by mechanistic models and so on, and backed up by empirical evidence with the machine learning algorithms. And this is usually a challenge that also takes place in environments that are very dynamical, so they involve complex and multi-scale processes, where data is sparse and expensive to acquire because it comes from sensors, it comes from simulations. For example, in some areas like material sciences, simulations happen on really huge H3C environments, and the data is very expensive. And they also occur in mission-critical areas where decisions have high consequence. So they can have severe outcomes. And for this reason, the models need to be extremely trustworthy. And to establish trustworthiness, ideally you would want to have explainable models. So models that domain expert can inspect, so they can look at their structure and understand what they're doing and why they take the decisions that they take. And another challenge is, of course, on the technical level, because there are, of course, numerical difficulties in optimization, almost always the requirement to compute gradients and to run code in HPC environments. So environments that are, for example, petascale machines, where you have to be very careful of how you implement things. Okay, so in light of all of the above, we can say that scientific machine learning entails kind of a focus shift from pure data-driven prediction to understanding. So understanding meaning that we need to extract insight from data by obtaining interpretable models, and the models themselves should conform to physical expectations, should incorporate physical laws, constraints, and other scientific domain knowledge. For example, they should have physically meaningful behavior and also physically meaningful parameters where this is the case. For example, Planck's constant, Avogadro's constant, and so on. And again, for the same reason that these are pretty mission critical, these models need to be robust, and we need to have the ability to quantify the uncertainty that they contain. This is all required for scientific rigor. So basically, scientific machine learning is an emerging field that is moving very rapidly, and it's trying to build a path from good science to good engineering with the help of machine learning and everything that this entails. So reproducibility, explainability, trustability, and so on. Now, you probably all know about the paradigms of science. So basically another take on this is that with the help of machine learning, we can basically move from the third paradigm of science, which is computational science based mainly on simulations, to the fourth paradigm, which is computational science augmented by artificial intelligence and driven not only by physical knowledge but also by data. So this kind of is the foundation of scientific ML. It needs to be domain aware, depending on the physical domain. It needs to conform to the physical requirements of that domain, which usually are physical principles, symmetries, invariances, other structural properties, and so on. It needs to be interpretable to help us explain and understand the models and get insight about the physical process. So this means that we have to be careful of the methods that we use and how we apply them to obtain models and how we do model selection and so on. And they need to be robust, stable, and to have some sort of reliability, quantifiable reliability to them. Starting from these foundations, of course, there are a few guidelines about what kind of capabilities should scientific ML include. Basically, this is a very data-intensive field, which means that it requires very solid inference and data analysis capabilities. It needs to benefit from algorithms that incorporate or integrate with simulation models and with simulation tools. So this is what we call surrogate models, so models that are developed by ML algorithms and that can achieve the same capabilities as simulation-based models, but usually with much lesser computational costs. And all of this needs to support intelligent automation and decision support. Okay, so there is a lot of research in this field, and of course a lot of approaches, starting with deep learning and with all kinds of methods that I some of them mentioned before. Basically, being a pragmatic field, it's always about performance versus transparency, aka explainability and interpretability. And these hybrid modeling approaches, which include physical knowledge, simulation-based approaches with, and combine them with machine learning, They're basically aimed to achieve high transparency, but also high performance. So they are basically trying to move away from this Pareto front here towards the upper right part of this chart, if you will. Okay, so if by traditional modeling we have, for example, approximate empirical models that approximate some data with not great accuracy, machine learning can help us to model some data very accurately, but we have to be aware that this may not be also physically accurate as well, or compatible with physical principles, like you see here in the middle chart with mathematical ML. And then this physically informed ML, which is basically the focus of scientific machine learning, aims to improve or augment machine learning methods, if you will, by combining traditional simulation-based and mathematical ML approaches in order to not only obtain accurate models, but models that have high throughput and performance and that have good generalization or extrapolation behavior. Okay. So by the way, you can see all the time the slides will be public, so I've put links, and so basically bibliographical references all over the slides. You can always look for more information. Okay. So a main focus of what we're doing here in Austria is symbolic regression, which is very critical for this physical-based approach to machine learning. The goal of symbolic regression is to find an expression, a function that matches the data from an unknown function. This is a core challenge in physics and engineering, and it's considered to be in principle an NP-hard problem. So there's no straightforward way of solving it with exact algorithms. So the space of symbolic expressions, so the possible combinations of mathematical symbols and operators, is a countably infinite space. So it's basically a very, very large combinatorial search space. It's discrete in the model structure because you can have many discrete structures, possible model structures, but continuous in model parameters, and it grows exponentially with the length of the expressions. So if you want to have longer expressions that have more modeling power and more capacity to achieve high accuracy, then you basically have to explore an exponentially growing search space. This problem can be formalized in the following way, so I'm just going to brush over this slide real quickly. I was talking about the search space consisting of possible mathematical expressions. This search space contains primitives, which are defined in a primitive set P and their operators. And this primitive set basically imposes a syntactic search space, SP. And then we can say, okay, in this search space we have phi, the space of possible expressions and their parameters. So a set of tuples consisting of a strictly syntactic structure of an expression and its coefficients theta. And we want to find algorithms that are very good at finding optimal models consisting of these tuples of E and theta. So let's call one of these tuples a symbolic expression model M of E and theta from, of course, the search space phi. And let's say we have a function G that evaluates this model on some training data. You're probably familiar with this concept, and outputs a prediction Y. So the overall goal of any symbolic regression algorithm is to find an optimal model by minimizing a loss function over this huge combinatorial search space. And an overarching objective of this is, of course, not only to get an accurate model that models the training data really well, but to achieve good extrapolation behavior or on unknown and even sometimes out of domain data. By the way, Andre, do you know how I can prevent this from popping out on my screen? It's pretty annoying. Okay. So what are some possible strategies to search this model space phi? We have evolutionary strategies, which mainly consist of genetic programming and grammatical evolution, but of course many others as well, which are basically in the category of guided Meta-Heuristics. Then we have generative and enumerative approaches, which try to generate, for example, mathematical expressions by repeatedly expanding production rules from a grammar, for example, a context-free grammar. These have the advantage of being deterministic, but of course, depending on how you define the grammar, you can obtain different results and different performance. So this is kind of in the category of guided heuristic. And then we have all kinds of hybrid methods based, for example, on divide and conquer approaches, on neural networks combined with other symbolic regression algorithms, and so on. And this is what I kind of call mixed heuristics. So apart from the strategies, I mentioned that each model, or rather each expression, has a associated coefficients vector theta. Strategies to optimize these coefficients are also very important, and here there are a number of approaches that can be used. For example, nonlinear least squares, variable projection, if the least squares problem is separable, stochastic hill climbing, and again other kinds of meta-heuristics. So as a kind of parenthesis here, what I really like about this field in general is that it brings together all kinds of algorithms and optimization methods that range from very principled approaches from the 60s and 70s, for example, such as nonlinear least squares, to very sophisticated algorithms like the latest in deep learning and so on. So on this note, I want to make a short detour here as an interlude. I mentioned already several times the words heuristics and meta-heuristics, but what does this really mean? So all of you are familiar with the concept of an algorithm, which is an exact, deterministic, correct, finite procedure, which is well understood, has proven complexity bounds, and gives a correct result for a problem. A heuristic is actually similar to an algorithm, but is not exact deterministic, not even guaranteed to be all the time correct. It's basically something that is derived from experience or from empirical evidence. It does not have such clear-cut theoretical properties that can be investigated. It does not have strong guarantees about optimality or complexity bounds, but at the same time, it's a very, very useful tool in practice. So they're useful practical solving tools that produce good results, not optimal, but close enough to the optimal in a short amount of time. So if you're interested, for example, in the history of this and why they're important, you can look at, for example, the history of algorithms that solve the traveling salesman problem or the subset sum problem, and you will see that there are great difficulties in pinning down exact procedures for this, and people always rely on very interesting and very ingenious heuristics for it. Now, what I really like, and this is from a paper from Fred Glover, the inventor of scatter search and taboo search from the 70s, is his really nice and almost poetic take on algorithms versus heuristics. So he says that algorithms are conceived in analytical purity in the high citadels of academic research. Heuristics are midwifed by expediency in the dark corners of the practitioner's lair. So this is a very nice analogy actually to our work and our industrial partners, because we are trying to illuminate these dark corners of the practitioner's lair. And the point, of course, is to make a profit. So we have every interest to midwife good results instead of achieving the highest achievable analytical purity. And also, I especially like the second quote here highlighted that algorithms are merely fastidious heuristics in which epsilons and deltas abide by the dictates of mathematical etiquette, and that they sometimes exhibit even a somewhat compulsive aspect. So what I want to emphasize with this is that heuristics are actually extremely useful tools in practice. And meta-heuristics also go along the same lines. A meta-heuristic is actually a guided iterative master process that coordinates a collection of subordinate heuristics towards the achievement of a certain goal. So it combines different concepts for exploring and exploiting the search space. If you're not familiar with these terms, exploration and exploitation, you have basically two kind of properties of a search algorithm. One is to discover new and promising regions of the search space, which to explore and investigate, and this is called exploration. And the other one is to exploit a certain region of the search space when the search procedure has locked onto it in order to locally improve solutions in that region. So this is what exploration and exploitation refer to. So it combines these concepts for achieving a balance between exploration and exploitation. It uses learning strategies in order to structure information. This is an important detail because many meta-heuristics include a stochastic component. So they use randomness as a kind of fuel for the search, but at the same time they are not random. So they use randomness, but they're actually quite learning able. So not like a random search or anything like that. They may manipulate complete or incomplete solutions or set of solutions, so local improvements of solutions, using heuristics to complete solutions and so on. Again, you can look, for example, at algorithms for the traveling salesman problem. And overall, they're basically quite useful optimization tools. They're usually inspired from self-organization and emergent phenomena in nature, in society. So people like to take inspiration from for meta-heuristics from everywhere. And this also kind of gets taken too far sometimes. So if you go in this link, you will see that there are a lot of especially nature-inspired meta-heuristics that are basically just for fun, let's say. And they kind of sometimes give the field a bad name. But overall, in order to achieve good results, especially in let's say, profit-oriented environments, meta-heuristics are invaluable tools for this. Okay, so we've already said about symbolic regression that it explores a gigantic space of possible mathematical expressions. How are these expressions actually represented on the computer or by an algorithm? They're usually represented as abstract syntax trees. So an abstract syntax tree is basically a construct which contains so-called internal nodes, which model the operators of the expression, and leaf nodes, which represent the arguments of the operators. And this abstract syntax trees, it's a concept that is basically ubiquitous in computer science, have a lot of nice properties. Basically, they are very easy to work with, they are easy to manipulate, they are easy to evaluate. You can write all kinds of interpreters and recursive procedures. They are quite amenable to automatic differentiation. This is important because, as I mentioned before, a lot of the work in scientific ML and in dealing with physics-based problems is computing gradients and Jacobians and stuff like that. So you can actually just use automatic differentiation using dual numbers, which are some numbers with a nice property that you can see here. And they can even be compiled to machine code. Maybe some of you have already heard of compiler infrastructures like LLVM or ASMJIT. or even to CUDA OpenCL kernels so that they can later be run on GPUs or FPGAs or stuff like that. They're also quite straightforward to transform. For example, taking an expression like this, which is basically a computational graph of symbols, you can apply all kinds of rules like algebraic rules or identities to simplify the structure, to bring it to a canonical form, to prune it, and so on. So they are very fundamental data types. The derivatives of such expressions can also be computed symbolically in case that you need to obtain a new expression representing the derivative with respect to a certain input of the original expression, and they can be easily tunable with algorithms like nonlinear least squares. For example, if I wanted to tune the coefficients of this expression, this would be the leaf nodes 2 and 5, and perhaps 2 and 5 are not the optimal values for this function, and they can be easily optimized. Of course, this is not a nonlinear expression, but you get the idea. Good. Now, I mentioned a few ways to approach symbolic regression. One of them is genetic programming. This kind of approach, this meta-heuristic, simulates the process of natural evolution. So basically the idea of the survival of the fittest. It can be described as a stochastic search guided by heuristics and the cost. By analogy with natural selection, this cost is called the fitness function, and it relies on heuristics which are called genetic operators, selection, so the analog to natural selection, crossover and mutation, and things like that get inspiration from the biological domain. The advantage of this method is that it's very general and it does not need any kind of a priori knowledge. So many regression methods start from a fixed model structure, and they seek to optimize its coefficients in a way that the error of the model is minimized. In genetic programming, the structure is not fixed at all, so there is no need to know anything a priori about the process, because the search itself can discover the structure, can perform implicit feature selection, and can find even optimal coefficients. There are several extensions to genetic programming. There are so-called memetic approaches, which hybridize genetic programming, particularly in the fitness calculation phase, with local optimization. So they include local optimization algorithms like nonlinear least squares based on all kinds of gradient-based optimizers and trust region optimizer and so on. They can be parallelized and distributed in interesting ways. So island models. In genetic programming, usually you start with a population of solution candidates which compete with each other for survival based on this fitness until the end of the process. And in an island model, you can have multiple populations. You can have several kinds of topologies between populations and communication schemes between them. And parallel tempering approaches are also a kind of topology like an island model, in which there are also aspects of simulated annealing included in the process. And of course, you can also have, as a third extension, some multi-objective strategies for genetic programming, in which case there is not a single objective to optimize, the cost function, but multiple objectives based on the specific modeling needs. It is very common, for example, to consider several objectives apart from fitness, so apart from the accuracy or model error, such as penalties in case the model has to satisfy some constraints, or even objectives that have to do with the parsimony of the model. So parsimony means the size and complexity of the model. In the interest of interpretability, we always want to have models that are small, but also that have very good performance. Now there are also some caveats or downsides of this kind of approach. First of all, it's non-deterministic. Like I said, it's fueled by randomness, which means that the entire process can give different results if you run it multiple times. It can produce overly complex expressions depending on the parameterization and depending on what kind of model complexity you are willing to allow in order to achieve, for example, a certain level of accuracy. And you always need to have some kind of trade-off between the model size, its parsimony and accuracy. Okay, now this is one example where genetic programming is used to fit a complex trigonometric function, and I will let you be the judge of whether or not this model is actually simple. You can see the structure here. So it's a parsimonious model, or it's a complex model that it needs to be simplified. For example, we can say that it has some nesting of trigonometric symbols. This is because this is actually a search procedure guided by the minimization of a loss function, and unless the user finds let's say effective and intelligent ways to constrain the search space, the hypothesis space of the algorithm, you can always risk to obtain models that on one hand model the data quite well, but on the other hand they have pretty huge complexity if you're not careful. Okay, now I've talked about genetic programming. I want to talk next about these so-called hybrid approaches, which include deep learning and other approaches. So my question to Andrei is that, do we want to have a 5-minute break now before moving into the part 2 of the talk, or should I continue now? All right, so we're back with the second part of the talk. What's left is now to discuss a bit about other approaches aside from Meta-Heuristics for tackling symbolic regression. So basically, when we're talking about neural networks or deep learning approaches that want to incorporate physical knowledge, these are basically called physics-informed neural networks, or PINs, and they are basically neural network approaches developed either to solve PDEs, so systems of partial differential equations, or to learn physical equations and physical laws and things like that. So there is the more general category of physics-informed neural network, which is basically a symbolic regression approach to learn equations. And then there are a number of more specific approaches that I will discuss today, like AI Feynman. So this is an algorithm developed at MIT, if I'm not mistaken, which uses all kinds of divide and conquer approaches and heuristics to learn equations. There is deep symbolic regression, which combines, actually uses reinforcement learning and the recursive neural net with risk-seeking policy gradients to generate these AST trees that we saw before. There is the equation learning network, or EQL, which does the same thing but using a different kind of neural network. And then I will say a few words about parsimonious neural networks, if I remember to include the slides, let's see. Okay, so what is the motivation for physics-informed neural networks? Basically, we have a black box optimizer, which is a neural network, and by default, this optimizer is not really capable of explaining anything from a physical standpoint. So the black box nature of deep learning hinders explainability and new scientific discovery. So there is this need to incorporate somehow the physical knowledge into this deep learning approach. So this is the so-called knowledge integration step. And this can be obtained in various ways. You can start even from basic feature engineering, from developing special network architectures that lend themselves very well to modeling some special kind of physical phenomenon. You can also use some kind of special loss functions that include regularization terms, and so on. So when you, for example, want to model PDEs, you are trying to encode them as part of the network itself. You are trying to incorporate as much of the physics of the problem into the architecture, and you are trying to incorporate other properties that pertain to knowledge integration into your loss function. For example, constraints, PD residuals, terms for initial and boundary conditions, and so on. A short taxonomy of this. Basically, you have on the left all kinds of neural network architectures, convolutional, recursive, and so on. Then you have types of knowledge representation. So basically in physics, by and large, everything is represented by differential equations, but you also have other ways to represent knowledge. And then you have the integration part, which includes all kinds of design choices, feature engineering, and regularization approaches. So this is a very, very general bird's eye overview of physics-informed neural networks. So in the regular, normal deep learning pipeline, you have to find a suitable integration point where you can take the prior knowledge about the problem that you have and put it inside the pipeline. So either by preprocessing, by designing the architecture in a certain way, or by defining the loss function also in a certain way. Okay. So in general, this is the kind of approach that physics-informed neural networks are taking. Now let's have a look at some concrete examples. First of all, there's AI Feynman by Odrescu et al. 2020. So basically there are two versions of this algorithm, version 1 and version 2.0, which augments version 1 with a bit of additional optimizations. And you can find the papers on arXiv, and you can also find the code on GitHub. I will also show some results of it later. Basically, this software package consists of a collection of heuristics for discovering physical laws. It works on symbolic expressions that are represented as computational graphs. It applies different kinds of solvers and problem decomposition heuristics recursively until it is able to decompose the original problem into a number of simpler problems and obtain a simple equation that explains the data. So overall, it exploits neural networks, graph modularity, hypothesis testing, normalizing flows, and all kinds of techniques to be able to achieve good symbolic regression results. So at the gist of it all is dimensional analysis, which tries to discover all kinds of symmetries in the physical law and, of course, in the data. So we have, for example, simple symmetry, additive separability, compositionality, and all kinds of other properties. This is an approach that was shown to work quite well on physics textbook equations, so equations that actually do exhibit these nice properties that are shown here. But what we've found is that it doesn't actually perform that well in the general case, where you can have all kinds of data from many different kinds of physical processes. So in the original paper, they tested this kind of physics textbook equations, and they obtained quite good results for them. So you can see there are all kinds of physical laws here on the slide. So I'm not going to insist too much on the details of AI Feynman, but as I said, it's really easy to find both the publication and the code. Another approach is deep symbolic regression, which is also kind of a very recent approach. The main idea here, so the strategy of exploring this symbolic regression search space, is to use a large model represented by a neural network to guide the search of small models, which are the actual symbolic expressions. So it exploits some kind of background knowledge from about the form of the expression, so it's an autoregressive procedure. It generates mathematical expressions using a recurrent neural network trained with a risk-seeking policy gradient, and also it represents the actual expressions as abstract syntax trees. So the structure of the tree can be actually mapped one-to-one to a sequential representation. In this case, they have chosen pre-order. So you can choose pre-order, post-order, breadth order, and so on. Okay, so how this works is that it generates this sequence of tokens sequentially by sampling from a distribution of tokens which is generated by the recurrent neural network with some constraints. Once a sequence of tokens is fully generated, so the sequence is complete, then it identifies the free coefficients of the expression and further optimizes them with nonlinear least squares. For the recursive neural network, it uses a so-called squashed reward function, R here, which actually includes the normalized root mean squared error, and the normalized root mean squared error is basically just the RMSE scaled by the standard deviation of the target variable y. So a picture is perhaps more valuable here. You can see that the inputs to the recursive neural network are actually parent and sibling pairs of symbols. The neural network then generates a categorical distribution of tokens based on this input. And then this distribution is sampled in order to actually fill in the tokens in the token sequence that will represent a abstract syntax tree. So this is an abstract syntax tree represented in pre-order, so starting root, left, child, left, and so on. And you can see here the final result, the expression tree. So in this case, the primitive set P of the algorithm is this library of symbols here. It uses arithmetic symbols, some elementary functions, and some leaf nodes. So x and y are the input variable and the target, and additionally some constants that are included in the structure and can later be optimized with nonlinear least squares. The algorithm is quite straightforward. So it consists of a number of steps, but it's quite runtime intensive as well because of the need to train the recurrent neural network. They actually applied this algorithm on a collection of rather, I would say, simple expressions. So there is the so-called Nguyen symbolic regression benchmark suit, and they have shown that a deep symbolic regression, so the first column here, is actually able to outperform other approaches, including genetic programming and including this commercial software called Eureka, which is considered by many to be the so-called gold standard in symbolic regression. So personally, I'm taking these results with a grain of salt, but this is one approach where you can use deep learning as a high-level guidance strategy for sampling this space of symbolic expressions. Okay, moving on, we have Equation Learner from 2018, which uses a fully connected feed-forward neural network structure, where the actual neurons in the network include base functions. So they represent the primitive set for the symbolic expressions. So they can be also arithmetic symbols, elementary functions, and so on. This feed-forward network consists of several layers. And basically from start, from input to output, the network generates a composition of base functions. And these are actually the expressions that are finally learned. So this approach was shown to be able to learn simple formulas and to be able to control, for example, a card pendulum system. Okay, so this approach is quite interesting. One problem that it has is with division, because division introduces discontinuities, so poles with abrupt changes in convexity. It introduces a divergence in the output of the network. So the authors went on with the assumption that because the data should come from a real, natural, physical system, this system should, behave in a natural way. So it should be unable to generate data at the pole itself, because natural quantities do not diverge. And therefore, they considered only a single branch of the hyperbola 1 divided by b, where b is a coefficient that is greater than 0. But for this reason, they're actually regularizing the division. So they are introducing a threshold for b called theta. And this division actually becomes a division between coefficients only if the denominator is greater than this threshold. And also they are using division only in the output layer of the feed-forward neural network structure. Again, a picture to better understand this. So X is the input, and then we have the layers of the network. You see that division is only present in the output layer. This kind of network is fully connected, but it's trained by stochastic gradient descent using mini-batches and Adam. And in the end, so the idea is that by training, the network will construct some paths, so some connections with non-zero weight, which are actually going to represent a simple formula, which will in no way be a fully connected computational graph of symbols. So in order to make all this work, they introduce a lasso-like loss function, which is differentiable in its free parameters, so the weights and the b's, and also a penalty term for small and negative denominators. Because remember, the denominator is supposed to be greater than a certain threshold and also greater than 0. So we have to penalize denominators that don't fulfill those conditions. You can see all this here in the expression of the loss function. The first part is the actual error term or cost, which is the norm between prediction and target variable. Then you have the regularization term, which is very typical to this lasso approach. And then you have here the penalty term. So you see all of this actually conforms to what I said before about pins, about physically informed neural networks, that they're trying to incorporate this physical knowledge either at the level of the features, at the level of the architecture, and at the level of the loss function. So it's also quite a principled approach, as you can see. Okay. Then there's also another type of network called parsimonious neural networks, also quite recent, from 2021. These networks, only a couple of words about them. They have been applied to learn the equations of motions of particles in the context of material science, and to discover melting laws from experimental data. So they obtain, of course, they use, of course, data from material sciences obtained from molecular dynamics, and they use some kind of evolutionary meta-heuristic to optimize the network structure and the weights of the network, which are also additionally optimized by backpropagation. They are using, so the main idea is that they have a preset structure or architecture. This architecture can include several types of neurons: linear, ReLU, hyperbolic tangent, and ELU. And they use an evolutionary algorithm to actually select the right kinds of activation functions to obtain networks that can learn these equations of motion, that can have good accuracy on the training data. So because of this space of activation function and all their possible combinations, you have approximately 10 to the power of 21 possible network structures, which are explored with the help of the meta-heuristic. So this is the generic network structure here. Then you have an additional inner network, which are actually just used to model the force. And this is preset and pre-trained. And the evolutionary algorithm is actually going to find the proper neuron types in this activation layer, so A1, 2, 3 to 6, and the weights, in order to produce a network that, a concrete instantiation of this template that is able to learn from data and to produce accurate results. Okay. So this concludes my overview of other hybrid approaches to symbolic regression. I just want to mention now that last summer I participated in a publication with some other authors where we tested all these contemporary symbolic regression methods on a large collection of benchmarks. And this is actually accepted that NIPS datasets and benchmarks track, and our findings were that except for special cases where the approaches are actually used to discover physical text pool laws, these deep learning approaches, so deep symbolic regression, you can see it here, DSR, there is also AI Feynman here, do not actually perform that well. So if you include, we had more than 100 benchmark problems. They overall did not rank that well in terms of extrapolation ability. So here we are showing the rank based on extrapolation performance and the actual median median coefficient of determination on the test data. You can see here the model sizes of the methods. So all the other methods are either evolutionary based meta-heuristics or general regression methods like XGB or AdaBoost or random forest and so on. And you can also see that in terms of runtime, these methods, so you see here the actual time axis is logarithmic, they are actually quite computationally intensive compared to the other methods. So that's why I mentioned in the beginning when I discussed deep symbolic regression that I'm taking the results with a pinch of salt, because our results did not necessarily put them in a good light. Okay. So the framework here, Operon, is our framework developed at the University of Applied Sciences in the Hill group. And it's basically an evolutionary system built on top of Ceres, which is a nonlinear optimization library from Google, Eigen, which is a linear algebra library, and TaskFlow, which is a parallel programming framework for. So all of this in C++. It's using also an AST representation as a post-order sequence of tokens, and it optimizes coefficients using the Levenberg-Marquardt algorithm. So you can see the full publication here as well as the source code here on GitHub. Okay. So this concludes the general overview of let's say physical-based modeling with a focus on symbolic regression. I would now like to give a couple of examples. So this is all relatively recent work that has been done not only by myself, actually. In the shape constraints, I participated, but it was not my main work. So it's recent research that tries to include physical knowledge in order to describe physical systems and discover conforming models that conform to physical expectations. So in general, shape constraints are a general concept which can be applied to different forms of regression analysis. Of course, not all methods are equally amenable to this. Symbolic regression lends itself quite well to this. The motivation for this is to ensure conformance to physical expectations. So for example, if you know that the model output needs to have certain properties like boundedness, non-negativity, non-positivity. These are properties of the function image, monotonicity, properties of the first derivative of the function, convexity or concavity, properties of the second derivative of the function. So this is a methodology to ensure that these properties are satisfied. We have tested several approaches. So this is work spanning 1 or 2 years. Not all of it is published. Some of it it's still in the exploration phase, such as interval arithmetic, which is considered to be a pessimistic approach because interval arithmetic tends to overestimate the bounds of the model, leading to false flags of non-conformance. Sampling the input space. So instead of using interval arithmetic, you're just sampling from the input ranges and evaluating the output of the model. Depending on the sampling, you may or not capture all the extrema points. This is why this is considered to be an optimistic approach. Then we also tried hard versus soft penalties. So these are terms that are included in the loss function of the optimization algorithm. So hard penalty, which means that a model would be rejected if it violates any of the constraints, while a soft penalty simply increases the cost or the error based on the violation and the quantification of this violation. And then we also tried single versus multi-objective approach. So this is, of course, an entirely different discussion, but basically, when you consider a single objective or loss function, you need to include all the other penalties and constraints in it. When you consider all of this as multiple objectives, then you have a little bit more freedom, and you also have the ability to generate a Pareto front of optimal solutions with regard to the objectives, and then you can finally select a compromise solution from that Pareto front based on the specific needs of the problem. So I'm talking a lot in general here because there's really a lot to say about all this in optimization. So what the actual goal of shape constraints is to model a function in a way that satisfies the physical expectance. For example, here you can see an unconstrained model output in the top figure. So the red dotted line is the actual function. This function is represented by data, which are these points here. And the green line is the actual model output, which interpolates these points. And you can see that although the original function is non-decreasing, the output of the model is decreasing in a certain region, which would not be realistic from a physical perspective. By imposing this shape constraints, which we can force the optimization algorithm to generate models whose output actually fulfills the constraint. So in this case, the output has to be monotonically non-decreasing. So you can see here that the model more closely follows the actual function. Okay. So another example here for a function with 4 variables, x1, x2, x3, and x4 on this chart, which we call partial dependency plots. The actual white area is the range of the input in the data that we have, and the red areas are the so-called out-of-domain areas, or areas where the model has to extrapolate well. And you can see here as well, if you consider the dotted line to be the original function, that some models, even though they interpolate quite well on the actual data they have been trained on, they are actually not able to extrapolate correctly. So in this case, you have some sort of parabola that goes down where it shouldn't. And for the 4th variable, you also have an unrealistic evolution of the output on an out-of-domain range of the input x4. So in this case, we know as well that extrapolation is physically not plausible, and of course, in this case, it's good to apply extensions like shape constraints that ensure physical plausibility. Now, another small parenthesis here. So I've talked about a lot of things so far, and I need to say that a lot of these are actually extremely deep rabbit holes that you can really get lost into, trying to explore deeper and deeper and try to find better and better methods to develop optimization algorithms. And it's always a compromise between what is theoretically achievable and what is actually practical to achieve. So I mentioned the pessimistic approach, interval arithmetic, which was a way to ensure the satisfaction of shape constraints. Interval arithmetic actually originates from the 60s or even 70s, if I'm not mistaken. It's a method for calculating output ranges of mathematical expressions based on the inputs. And it consists of several rules for computing these output intervals, depending on the arithmetic and elementary operators that are contained in the expression. Intervals are represented as endpoints, A and B, so basically a set of points between these endpoints on a real axis. Interval arithmetic is quite helpful because, for example, if you're using it in a constraint satisfaction sense, or even in robotics, in collision detection, or in gaming, you have basically 2 cases. The output of your model is outside the bounds predicted by interval arithmetic, and then you know for sure that the output is wrong, or the output of the model is within the bounds, and you don't know for sure that the output is wrong, but you know that interval arithmetic overestimates the bounds, so it might be wrong. This is due to a fundamental weakness in interval arithmetic, which is that it does not track dependencies between operator arguments. So for example, if I have a function that takes arguments x and x somehow, then interval arithmetic by default is unaware that there is a dependency because it's the same x. So if you look at these examples, for example, if you have x minus x, which with x in a certain interval, a to b, by applying the rules of interval arithmetic, you would obtain an output range consisting of the endpoints a minus b and b minus a, but we actually know that x minus x is always 0, so the actual range is 0. In the second case as well, if x is bounded by minus 1 and 1, we have this expression x squared minus x, and we know that the actual output range is minus 0.25 and 2, but interval arithmetic is unaware of this, and that outputs the range minus 1 and 2. So in both cases, we are not that far off from the truth, but we are indeed overestimating to a certain extent. So actual conforming models, if we're not careful, might get discarded because of this overestimation. Now, as it is in computer science, there are actually ways to overcome this problem, but only if we are willing to pay the computational cost for it. So interval arithmetic is based on some basic properties that come from interval analysis. Some arithmetic operators are commutative and associative, like addition and multiplication. Some other operators are subdistributive, so this is a weaker form of distributivity. For example, if you have this expression here, expanding it will give an output range that would include the original output range. So according to what interval arithmetic outputs. Then we have some properties depending on the monotonicity of the function. So of course, if f is non-decreasing, then it's bounded by its values in the infimum and supremum of the input, points in the input range. And there are this also nice properties of inclusion, isotonicity, and interval extension. So all of this, without going into too much detail, means that interval arithmetic is actually benefiting from a nice property thanks to inclusion, isotonicity, and interval extension. And that is that if you take the input space, which is actually bounded to a d-dimensional box, the box defined by the Cartesian product of all the input ranges. If you discretize this box and apply interval arithmetic and calculate the output on the very many discrete parts of the original box, and then compute the union of the discretized results, you can obtain a much more accurate result. And we have actually implemented a number of approaches for this, greedy approaches, branch and bound heuristics, that are able to greatly improve the accuracy, but unfortunately, of course, they run much, much slower because they have to discretize the original box into very many smaller and smaller pieces. So this is an example here where you can see for a certain function that applying certain approaches, you can actually refine and tighten the bounds given by interval arithmetic for the expression. This is actually a very useful tool in our toolbox, and we have applied it to generate physically conformant models that model physics textbook equations. These are actually taken from the Feynman Symbolic Regression database created by Udrescu and Tegmark, so the inventors of AI Feynman. You can see here some examples of expressions from physical textbooks and the constraints that we used for the inputs and for the derivatives of the model and so on. I want to show some work from us Of course, the idea of shape constraints is much older, and we did not invent it. We just applied it to symbolic regression in order to obtain physically conformant models. This was work mostly done by Gabriel Kronberger, Christian Heide, and Fabrizio Olivetti de Franca, a professor from the Federal University of ABC in Santo André, Brazil. You can find the publication here. What we tested was the ability of symbolic regression to generate physically conformant models while achieving high accuracy. We compared different methods and we obtained some kind of mixed results. Shape constraints do ensure conforming models, but at the same time do not necessarily offer better generalizations. So this is a topic where I believe further improvement is possible in order to obtain better models. However, there is a slight silver lining, which is that shape constraint models actually do perform better on noisy data. As you know, data that comes from actual industrial processes sometimes includes a fair amount of noise. So there is actually applicability for this. Okay. And now, because I'm stretching this talk a little bit too long, I will move on to the next example, which is something that I've worked on in the first half of 2021, so for about 6 or 7 months, which is using symbolic regression to model potential energy surfaces in material science. So the motivation for this is that in order to investigate new materials and their properties, you have to perform really large numerical simulations, which are based on two main frameworks, molecular dynamics or Monte Carlo simulations. And in order for these simulations to give accurate results, they need a realistic model of the interactions between atoms, the so-called interatomic potentials. And what we want to do is to generate, using machine learning, surrogate models for these potentials that are accurate and are much faster to compute, which enable these simulations to model larger systems and to run for longer timescales. Okay? But these interaction models have to be really accurate in order to enable reliable outputs. There are several approaches to model these potentials. There is the empirical or classical approach from physics, from first principles, which is fast. It consists of simple analytical formulas, but it's not very accurate. Then there are the so-called quantum methods, like density functional theory and others, which are very accurate but very slow. And then, of course, there's machine learning, which uses data generated from the previous methods, especially quantum methods and DFT, in order to generate surrogate potentials. So a potential energy surface is actually a mathematical construct that describes the relationship between atomic positions and their potential energy. So in a material, the materials move around and wiggle and rotate and so on, and their potential energy varies based on the configuration of atoms, and we want to predict how exactly it varies. So machine learning recently emerged as a means to model these potential energy surfaces at lower computational cost. You can see here a chart of the actual existing methods and their costs. So classical empirical potentials are fast but are not accurate. And as you move towards more and more accurate models, you see that also the cost increases very, very much. You see here the cost axis is logarithmic, and it goes really, really up to this insane n to the power of 7 complexity. So this is the main limitation, which actually very much limits what can be achieved by numerical simulation. You can also see a bit of hidden information in this picture with The faster your model, the larger the system that you can simulate, and the slower your method, the more limited the size of the system that you can simulate. Up to, for example, DFT, which can only simulate, I think, recently only systems up to 100 atoms in size. So this is where machine learning promises to revolutionize material science by introducing the ability to simulate these potentials at much lower cost with high accuracy, and thus enabling larger systems to be numerically simulated. Okay? So there are, of course, some general requirements which are hard to achieve by machine learning potentials. They have to be generally applicable so that they can be transferable from a quantum chemical system to another. They have to be sufficiently accurate compared to first principles methods, and they have to be highly efficient to enable these large simulations. And of course, there are some other nice properties, including the ability to provide physical insight. So this is a very rapidly moving field. Papers appear almost daily with new algorithms, new methods, new ways to extract knowledge. Currently available potentials are actually far from satisfying all of these needs. This is a small schematic where you have here traditional potentials on the left, which is a formula derived from physics, which is parameterized, and it's not very accurate. Then you have machine learning-based potentials, which are based on structural parameters. So the input data for modeling a potential energy surface is simply a list of atomic coordinates within the material that we're studying, along with some other information like moments and forces. So you can get those coordinates and try to learn from them. And then you have physics-informed ML, which are actually trying first to map the structural parameters using regression to physically meaningful parameters that are actually put into a physically plausible model to model the total energy of the system. So here, each atom has a certain radius because the potentials are so-called short-sighted. They only are influenced by the nearest neighbors. And based on this radius, we have the structural parameters of the neighbors, and we are learning from them. Okay? There's a lot, and really a lot of research going on into trying to map the structural representation of Cartesian coordinates into other kinds of features, which are actually called descriptors in material science, that enable or empower other types of machine learning algorithms to obtain good results. The main difficulty here is that these atomic systems, they need to have some really important physical properties like symmetry, permutation invariance, translational and rotational invariance, and so on, which is why it's very difficult to map the raw electronic structure data in the form of Cartesian coordinates to proper features that are usable by a machine learning algorithm. There are many approaches for learning these potential functions: neural networks, polynomial fitting, a recent one called moment tensor potentials, which is very successful, and so on. But there are ongoing issues of generality, transferability, conceptual problems of incorporating all the physical properties, as well as the difficulty in obtaining models that are not too complex and are actually explainable and interpretable. And another issue is, of course, that all these methods require varying amounts of training data, which is expensive to obtain because it comes from quantum mechanical simulations. Okay? So recently, there is an emerging need for explainability in this field, which is why black box methods, although they are prevalent right now, are not really always the most suitable. They have almost zero capability of including physical information into the model, they must rely almost exclusively on the physics-inspired features, so the descriptors derived from the raw electronic structure data. And for this reason, they require larger amounts of training data, and they return models that are more complex and slower to evaluate. And white box models like symbolic regression are kind of emerging as an alternative to black box methods because they provide an analytical equation. Even if its structure is not always simple, it can be investigated, and they're more amenable to the integration of physical knowledge. Even at the most basic level, by restricting the hypothesis space and the primitive set, you can already, as it has been shown, obtain physically plausible potentials. Okay? So the training data comes from quantum mechanical simulations, which consist of snapshots with atomic positions and energy. They are usually provided in special formats generated by very special software. So for example, the Vienna ab initio simulation package. And each actual so-called data row or observation is actually a set of coordinates describing atomic clusters and an energy value. So this gives rise to some kind of difficulties in integrating this as training data. There are some promising symbolic regression approaches recently, which use pairwise atomic distances from the original Cartesian coordinates, filtered by inner and outer radii, so to consider the neighborhood of each atom, and in the end they give the total energy as a sum of energies for each considered atom in the cluster. So you see again, they return abstract syntax trees as the models with some special symbols inside. And these guys, Hernandez et al. In 2009, were actually able to obtain accurate and transferable many-body interatomic potentials for certain kinds of chemical systems. And with this, I conclude my talk. I wanted to talk about scientific ML and basically machine learning becoming a critical part of the fourth paradigm of science, which is physics-informed machine learning. So SciML is an emerging field focusing on applications in computational science. These are more restrictive than the general classification or computer vision or other stuff because of the need to have physical plausibility. This is why explainability and interpretability are increasingly important, and this is why existing methods have to be extended and modified and made to incorporate physical laws and physical knowledge. And of course, all of this is closely related to engineering domain and usually runs in performance critical environments. Okay, with this I would like to close my talk and apologize for taking too long. And I'm always open for questions. I think we have some time now, or if not, you can always send emails or visit our website and get in touch. So thank you. Any questions?
Hi, Bogdan. Thanks for the thorough presentation that you did. I'm curious if you, for example, I have some experience with this kind of modeling, but in practice, I mean on real problems that are not textbook problems, such as the AI Feynman was trained on, or basically trying to figure out some things like, I don't know, what's the equation of a spring or something like this, which would be very easily from the data, or the Kepler's law of planetary motion. Have you, because I haven't seen it mentioned by you, have you heard of PyCindy? module?
How? Sorry? By?
PyCindy.
Ah, yeah, I've heard of it, but I've never used it myself.
Yeah, okay. So, yeah, what I want to ask you is, have you used this kind of modeling in practice on some real problem? Like, I don't know, you have some scientific application in which you get some data. For example, I just made a practice at some point to just check if there is some symbolic representation of the data, but it didn't. I never found one. Obviously, there might not be one, or the data is very bad. But generally speaking, have you used it, for example, in some kind of applications?
So I have not used this PySynth specifically, but I have used software in this general direction, even software written by myself, and my colleagues have used as well. And I think this kind of work has been part of our contracts with various industry partners, but the results are their respective intellectual property. So I wanted to actually give more details about our partners, but all I can say is that we did, they incorporated our results, they were happy, they paid us, but that's all for now.
Okay, so when you say you basically found some symbolic expression of the data?
Yeah.
Okay, yeah.
So for example, you can have a physical model of some process like deformation, and the model is parameterized with some coefficients, but the coefficients are not the same all the time because the system has different operating regimes and maybe some other different, let's say, ranges of operation. And in this case, one approach was to replace those coefficients with symbolic models that react to some other information in the environment, and this kind of augmented the original physical model and allowed it to obtain better results.
I see. So in a way, so another question is, did you cooperate with experts in the field? So like there was some kind of inductive prior to this whole approach?
Yeah. And sometimes the experts even said that, okay, we see that this model is accurate, but it makes no physical sense, so scrape it and start again.
I see. So basically it had no explainability, let's say.
Yeah, so usually in the type of cooperation when our group consults for a company, there is always this development cycle which includes domain experts that give all the time feedback, so that the results are actually conforming to the expectations of the company and of the physics and all that.
I see. Well, it makes sense. I mean, for example, if you're trying to discover some, I mean, it's pretty hard to narrow it down. I'm thinking about it right now. So if you get an expression, how do you know it's a bad expression if it has predictive power? Just because it doesn't have some exponential function in it as you expected it to have, or something like this.
It's not always as clear, and also because some of the processes, for example, I mentioned in one of the first slides, plasma nitriding process. These are highly nonlinear processes, and they depend on a number of factors, like, I don't know, voltage, plasma temperature, and some the actual chemical composition of the gas inside the plasma, and things like that. So it's really, really difficult to model. And in this case, what we can do is to provide some sort of, let's say, AI-based suggestions, and then the domain experts may make informed decisions based on their knowledge and also based on what the AI says. But it's more like let's say an AI that would assist a doctor in giving a diagnosis than an AI that would explain a disease or something.
I see. Well, it makes sense to me.
So we often provide some custom software solution that that does this for the clients.
Okay, thank you.
You're welcome.
Can you hear me?
Yes.
Oh, okay, I can hear you now. I was trying to speak earlier, but it looks like Zoom is not in its best shape today. Had to restart it. So thank you, Bogdan, for a really nice presentation, interesting, full of scientific stuff. Really exciting. It was exciting to me. I also have a question to you. This symbolic regression back in 2008, when I first took my practical experience with the machine learning and looking on how multi-layer perceptrons can simulate these non-linearly separable functions like exclusive disjunction. I've wondered why we should simulate them using such structures like layered networks when we can directly put some more complex functions in a kind of regression tree and a decision tree and get a smaller and more straightforward predictive model, right, to approximate a function. And I discovered then that the symbolic regression actually, I mean, I was not the first one who thought about this, and it was a whole domain there. And symbolic regression, there were not too much research papers, but there were few. And despite of the fact that it looked so simple and straightforward, when I've got to try to train to learn create such a model, it was really hard. And even you have shown in one of your slides how the modern symbolic regression approaches are not able easily to emulate a bivariate polynomial. You had a function there, x with y, right? A simple bivariate polynomial which a modern neural network can approximate it quite easy, right? So, and there, at least at that time, there was a huge gap between the symbolic regression and the neural networks, even if they were not so popular like they became in 2012, right, with the ImageNet. But still, even now, in the community, there is, as far as I know, this skepticism that the symbolic regression might be a solution to real life problems aside of these physical simulations or physical related problems. I took a look over your paper with those 122 data sets that you've shown also in one of the slides, where the how this method called sorry, I just forgot it, which actually shows how it's called. Just a second.
I moved back on the slide.
Operon.
Yeah.
Yes, yeah. Like it beats all the other regression methods on that not data set, that set of data sets, right? 122 different data sets extracted from real life. Like, could you give us some examples where this approach might be useful in a business or common industry problems other than physics? If you have experience or have seen any papers saying that.
Yeah, that's actually a good question. So, first of all, I think I would start by saying that, yeah, the multi-layer perceptron is what we call a universal approximator. So it is theoretically proven that it can approximate any kind of function, which is why in theory you cannot actually beat it in accuracy if the network is large enough and has a sufficient amount of training data. But the problem actually with neural networks comes from this distinction between black box and white box, or some spectrum of gray box methods, because symbolic regression cannot beat other methods in terms of pure accuracy, that's clear. And so other methods like neural networks or random forests. But it can be useful when you actually want to get any kind of insight, no matter how tiny, into the actual process. Because if you look at, let's say, the network and its weight, you cannot really learn much about it. But if you look at the model, even if it's not so simple, you can actually learn maybe some basic dependencies between the inputs, maybe some underlying pattern that governs the data. And this can help to understand the process a little better. At the same time, for neural networks, you are responsible for preparing your data in a proper way and doing the actual pre-processing and data science part before to ensure good results. While these methods based on symbolic regression are a little bit more general in the sense that they perform implicit feature selection. So again, they can be used as a way to determine which inputs in your data, which presumably corresponds to some variables or factors influencing the process we are modeling, which of them are more important and which kind of interactions they have with one another. So in a nutshell, I would say, okay, it's a method that can deliver good results, but its main usefulness is in helping to gain insight into the process.
So when you need explainability of the model, that case.
Yeah. So maybe not full explainability, but like I said, you can get a gleam of something, an insight about something that maybe about the process that maybe you aren't able to get otherwise. So it's a question of degree, but yes, explainability ultimately.
And an example of applicability in real life, maybe one of those data sets which might give us some a feeling about where it works good. Like it works in regression, right? I'm not sure, but I think it also might be as well used in classification, in even multi-level classification, like logistic regression. You just can apply activation function there, and you can
yeah,
use
so it works in regression and classification, and if we're talking about genetic algorithms in general, they are being used successfully in many other fields.
So one example of the problems which Operon solves better than the other approaches.
So Operon is just focused on symbolic regression. So its main strength actually comes from the fact that it integrates with a very robust nonlinear least squares method and with a very robust automatic differentiation mechanism. And so it's able to get kind of the best of both worlds. The best of an optimizer that is based on gradient descent, combined with the best of an optimizer that is based on Meta-Heuristic, so has the flexibility of exploring very large search spaces. I'm not sure if I can come up now with a concrete example, so it's basically only for regression at this point. I've used it successfully to model interatomic potentials. The code for that is not yet published because it's not yet mature, but it will come up at some point on our GitHub. And let's say I've used it, let's say more esoterically, to model computational complexity of an algorithm after instrumenting the algorithm and generating a large amount of data. So data like branches, loops, iterations, and so on, and it obtained for me a really nice symbolic expression, simple, of the big O complexity formula. And I'm not sure if I can think of other examples from the top of my head.
Would it work, for example, for the weather prediction? I'm looking into this paper. There are like over 100 of real-world data sets and problems. Wind prediction. Maybe you have worked at least once or have heard of anything other than physics. Our community, most of us are working in industry of IT, and our work mostly is related to a way of making producing an efficiency in businesses. So some examples from this side of things and this industrial, let's say, might be helpful to us, to our audience.
Okay, so Operon is a relatively new framework, but it's heavily inspired by Heuristic Lab. I've worked on Heuristic Lab for 10 years now. And Heuristic Lab has been used to solve all kinds of problems, for example, with data coming from sensors. So in the area of fault prediction, predictive maintenance. I believe this is the direction you are suggesting. So it has been used on all kinds of data coming from all kinds of fields of industry and engineering, as well as, like I mentioned, predicting cancer based on tumor markers, predicting blood glucose levels from the top of my head, modeling dynamical systems, like for example PDEs with pendulums, or describing pendulums, or the Lotka-Volterra equations. Now I'm orbiting back to the physics a little bit. So in general, we used with Heuristic Lab symbolic regression with all kinds of data. I think even financial market forecasting and things like that. But I don't know all the examples from the top of my head. You can find probably a lot of information on the website.
And there is an implementation available in public of this Operon framework?
Yeah, it's on GitHub, and most of everything we do is open source. And also we strive to get in line with all the open access directives of the EU. So you are likely to find a lot of stuff. So not to mention the code, which is on GitHub and on our for now still Subversion repository for Heuristic Lab, but also publications and stuff like that.
So we can draw a conclusion that if I have a regression problem, one of the first things I should try is also this Operon, as the training time is not so big. It's comparable with the XGBoost as far as I can see, and but it has superior accuracy with a very small model size.
Yeah, so what I would say in general is that there really are no silver bullets in this field, in data science in general, or in AI. I, for example, like to use whatever works best. There are always different kinds of tools, and it always depends a lot on the actual application. So sometimes it will be Operon, sometimes it will be something else. I've worked with pretty much everything. I've implemented myself just to learn even neural networks and support vector machines and other stuff. And in general, every time you approach this problem of modeling something, there is an exploration phase where you try everything and see what works.
Mm-hmm. Okay, I see one very clear winning of this approach is the size of the model, which might be interesting for edge computing, for the small devices,
Yeah.
right? And IoT, as I guess the inference of the prediction is lightning fast, right? It takes small amounts of memory, and it might be very suitable for such cases on IoT stuff, on Raspberry Pi, on small computers.
Yeah, this
Is
was
that
actually
right?
one of the design goals, which is why it uses some really bare metal C++, if I can call it like that. So efficiency is, it was a goal, and I can imagine it running on all kinds of small devices.
Okay, thanks.
You're welcome.
Anybody else has any questions? Please don't be shy. We don't have every day Bogdan with us. I guess you have a Slack account, right? And
yeah, I'm on all the Slack groups, IAFTI and the other ones, the Romanian ones, and you can find me. I'm quite easy to reach on several platforms.
Perfect.
As long as it's not social media. So.
Okay. So, any other questions? Any comments on the presentation? Okay. So I guess that's it. It's already 8 o'clock. I will stop the recording.
Yes, I recorded as well with